Welcome to my PyCon 2020 talk entitled Beautiful Python Refactoring. My name is Conor Hoekstra, and I go by code_report on Twitter and YouTube. A little bit about me before we hop into the talk. I'm a senior library software engineer working for NVIDIA on the Rapids AI team. Our team is developing a end-to-end data science pipeline that runs on the GPU. So if you're interested in checking that out, check us out at rapids.ai. I am a programming language enthusiast, so my majority of my experience is in C++ and Python, but I'm actively learning several other languages at all times. The team that I work on primarily uses C++ 14 and Python 3. I love algorithms and beautiful code. I have a YouTube channel at youtube.com/codereport where I solve competitive programming problems in a variety of different languages. So if you're interested, check that out. And as I mentioned before, my alias online is code_report. So if you're trying to search me, sometimes that's easier than searching my name. So why am I giving this talk? Approximately half a year ago, or maybe later, depending on when you're watching this talk online, I joined the NVIDIA Rapids team. Specifically, I work on the cuDF library. So there are multiple libraries that exist within the Rapids organization, or that the Rapids organization is working on, and I work on the cuDF library. So the Q in each of these libraries comes from CUDA, which is the parallel programming platform and programming model, or at least that's what the online website says. I like to think of CUDA as the programming language that you can use to do GPU computing. And the DF in cuDF stands for data frame. So there are typically two data frames that I know of. Obviously, the cuDF library, because that's the one that I work on, or the team that I work on develops. And the other more widely known data frame library is pandas. So if you're not familiar with pandas, the one-line description from their website is pandas is a fast, powerful, flexible, and easy-to-use open-source data analysis and manipulation tool built on top of the Python programming language. And the one-line description of cuDF is that cuDF provides a pandas-like API that will be familiar to data engineers and data scientists, so they can use it to easily accelerate their workflows without going into the details of CUDA programming. So the data frame Python API is modeled very closely on the pandas API, so that data scientists that are familiar with working with pandas will find it very easy to transition to the cuDF or Rapids data frame library if they need to accelerate the data science that they are doing. So when I started back in October, I thought that it would be good to familiarize myself with the pandas library. So I decided that I was going to work on a small toy project that could use pandas to manipulate some data or analyze some data so that I could get familiar with pandas. So I decided that what I was going to do was analyze the data that is on one of the competitive programming websites that I occasionally compete on and cover on my YouTube channel, that is Codeforces, and they give you data on the number of submissions, whether they're successful or they fail, and what I was most curious about, which was the language that you are submitting it in. So the question that I came up with was, what are the most popular programming languages used on sites like Codeforces? So for this talk, I'm basically going to show the steps that I went through to get that code working. And throughout that process, I ended up refactoring a lot of code that I had pulled off of a website and from a blog in particular. And I think it is going to be really illustrative, and hopefully you'll find it educational and be able to learn from a few of the refactorings that I did and improve the quality of the code that you're writing on a day-to-day basis. So how do we go about doing this? It's really only two steps. The first step is to scrape the HTML data from the Codeforces website with pandas. And the second step is to analyze that data with pandas. And once we're done those steps, we're done. So for the duration of this talk, 90% of it will take place in step number one, because that is where all of the refactorings that I did occurred. But I'll also spend the last 10% of the talk showing you the analysis with pandas, just to motivate why you might be interested in picking up pandas or a library like cuDF. So how do we go about scraping HTML with pandas? I had no idea, so what does any engineer do when they have no idea? They go to Google and they type in what they'd like to do, scrape HTML with pandas. I did this, and in the second result, I found web scraping HTML tables with Python that had a reference to the pandas data frame in it. So I opened that up and I got to the following blog. And this blog takes you step by step through how to set up a piece of code that will basically scrape the information that you want from an HTML table. So I went through this, and at the end of it, it's about 60 plus lines of code, depending on how you look at it. And we're going to quickly go through and sort of highlight each of the sections of that code that they sort of break apart in the blog. So the first section is the imports, which is pretty straightforward. Nothing really we need to talk about here. Requests is for getting the HTML. LXML is for being able to parse and read the HTML. And then pandas is for the data frame that we're going to set up at the end. The second section is initializing the page, doc, and tr elements that we're going to use to do the scraping. After that, we have our first for loop, which is used to extract the titles from each of the columns in our table that is on the Codeforce's website. The second piece of code that involves for loops is two nested for loops, which is used for basically extracting the contents of our HTML table in each of the columns of the table. And then at the very end, we construct a data frame from a dictionary that is constructed using a dictionary comprehension. So the first piece of code that we are going to look at is going to be the first for loop that I showed you. So here we have initialization of an empty list col and an index I. And then we have a for loop that goes through each one, reads something from each element of our tr elements data structure, and then appends it at the very end. So we're going to remove the comments here. One, primarily just to make the text bigger, but two, because these comments are a little bit redundant. We don't really need a comment to tell us that we are constructing or initializing an empty list here. So we remove the comments. And the first thing that we notice about this code is the following pattern. We are initializing an index I, then looping through each of the elements in our tr elements first row. And then right after that, we're doing an increment to our index. If you ever have this pattern where you're initializing an index outside a loop and then inside your loop incrementing it, there is a function or an algorithm for this in Python called enumerate. So using enumerate, we can basically remove the initialization of our index and the incrementing of our index and pass our tr elements first row to enumerate. And then using destructuring, we can destructure the now zipped indexed with each of our elements in tr elements into I and t. So I will be our index and t will be the elements that we were originally getting from our tr elements first row. So this is an algorithm that's known by a couple different names in different languages if you found yourself at this video as a not a Python programmer. So it's primarily known as enumerate in languages like Python, Rust, and D. But in other languages, it's also known as with index in Ruby, Kotlin, and Elixir, and also as indexed in Racket and Haskell. So this is a very, very useful algorithm. I've seen this pattern many times where people are initializing an index outside a range-based for loop that doesn't give you the index, and then they're incrementing it inside the for loop. If you can, if your language has it, and Python does, try to make use of this enumerate. So the second thing that I noticed was that the index that we are now getting from enumerate is actually only used in one place, and that's in this print statement. I'm not exactly sure what the initial purpose of this print statement was, probably for debugging purposes. It's supposed to be sort of a teaching blog, so my guess is this was to make it easier to understand for the individual putting this code together. But at the end of the day, you don't actually need this print statement. So the second refactoring that we can do is just to delete the print and then the enumerate that we just added. And that will look as follows. And at this point, we can start to see that we can actually probably change this for loop into a list comprehension. So if we get rid of the name variable and put the t.textContent directly inside the append call, you can see that this is really doable in a list comprehension, which is going to be our third change. So list comprehensions give you the ability to basically construct a list in place without having to violate what I call the ITM anti-pattern, which is my least favorite anti-pattern that I see all the time in code. So once again, ITM, this is an anti-pattern that you should try to avoid at all costs, and it is my assertion that if you can avoid this anti-pattern, your code will become more readable, more maintainable, and just better in general. So ITM, it stands for initialize, then modify. We've seen it twice already. The first example was when we had the code that could be replaced by a call to enumerate. Here, we're initializing the index I, and then inside the for loop, immediately modifying it. We can avoid this by using enumerate, and in my opinion, it makes the code easier to read. The second example where we saw this was in the code that we just saw, where we're initializing column and then immediately inside our for loop, calling the append method on that list for every iteration of our for loop. We can avoid this, as I just said, with a list comprehension. So if you can, try to avoid the ITM anti-pattern. It leads, like I said, to, in general, better and more readable code. So moving on to our second set of for loops that we're going to look at in Refactor. This is the code that is responsible for basically extracting the data from the columns of each of our tables. So we're going to look at this nested for loop bit by bit, and the first bit we're going to look at is this if statement sort of on the third and fourth line. So here it says that if the row size is not of size 10, that means that it's not from our table. When I ran this on the Pokemon dataset that originally came with this blog, I didn't run into this, and I'm definitely not going to have this issue with the Codeforces data, so we're able to just delete this if statement. This won't always be the case when you're refactoring, but for your use case, if you find that this is the case, you can definitely just remove redundant code that's not doing anything. The second change that we're going to make to these nested for loops is by taking a look at the first two lines of our first for loop. So here we have for j in range 1 to the length of our tr elements list. And we're then using that j, which is going to be an index, to assign t to be the jth element of our tr elements. So this was a bit confusing to me when I first looked at it, because I thought, why aren't you just looping over the second to last elements of tr elements? But I figured that would be because we actually need tr elements again. However, when I looked at where tr elements gets used, it's only in the first two lines. So it became obvious that we're able to use something called slicing here in order to avoid having to use the range function, calculate an index, and then indexing into tr elements to set t. We can just use slicing to immediately set t in our for loop. So that looks as follows. We use slicing to basically drop the first element of our tr elements list, and this is going to give us the second to last elements in our list tr elements. So this is exactly what we want, and we are able to avoid not only a second line of code, but also a call to the function range, which is fantastic. The next thing we're going to look at is a pattern that we've seen before. Hopefully you were able to identify it. We're setting an index I inside of, and then inside a for loop, incrementing this index for each iteration of the for loop. Hopefully you remember what we did earlier, and that is making use of the enumerate function. I said it before, but I see this pattern all the time. And when you're in a language like Python that has this algorithm or function, it is a godsend. In certain languages like Go, they actually have it built into their range-based for loops, which is a really, really interesting design choice for the language. But yes, use this when you can. It makes your code much more readable, like I said, and it avoids the ITM anti-pattern. The next change that we're going to make is taking a look at another if statement. Once again, this if statement says check if the row is empty. I ran this on the Pokemon dataset, didn't run into any of these cases, and also it's not going to be an issue for my Codeforces data, so this can be removed the same as we removed the previous if statement. The next piece of code that we're going to look at are the 4 lines in the middle. that are the try and except. And if we read the comment above these 4 lines of code, it says convert any numerical value to an integer. I don't think that this is the best way that we could be doing this. I try to avoid try and except statements when possible. So the way that we can improve this piece of code is to use something called a conditional expression. In many other languages, you can get the same effect by using something called a ternary operator, which is typically the question mark combined with the colon. But in Python, it looks as follows. It basically enables you to do assignment based on a conditional statement, but it combines it with sort of an if and an else, so it becomes an expression. So the way that it reads is basically value 1, if conditional, else value 2. So if the conditional is true, it uses value 1, otherwise it uses value 2. So here to set the data, we're basically casting our data to an integer if the data is numeric, otherwise just using the piece of data. So I like this better than the previous code because 1, it's a single line, but 2, it avoids the try and except, which I think you should try to avoid if possible. And once again, I just really like avoiding the ITM anti-pattern. Technically, we are modifying the data here, but in the next couple of changes, we're going to avoid that as well. So the next change is to remove the redundant comments. So if we read the 2 comments here, the first one is to iterate through each element of the row. I think any comment above a for loop that is just saying we're iterating through each element of insert what we're iterating through, this isn't really adding any value as a comment. Similar to the second comment, append the data to the empty list of the ith column. This is pretty self-explanatory by just reading the fact that we have a 2-dimensional list and we are appending to the ith column. So we can remove both of these. And also, like I said, remove the second assignment to data and just put that code in the append method that we are invoking here. And at this point, we are going to stop and just see how far we've come. So if we go back to what we originally started with, we had roughly 60 plus lines of code. And at this point, we're down to about 20. So we've eliminated 2/3 of our code. If we reformat the comments on the first 4 lines, we can even get this a little bit more compact, which I prefer. And at this point, we have all of our code on a single slide, which makes it a little bit easier, or a lot easier, to reason about holistically. And we can start to notice something about the code structurally, and that is that we are initializing our list of tuples, COL, to initially have the title of our column as the first element of each of the tuples in our list. And the second element is just initially empty. And then in our nested for loops below, we fill the contents of these empty lists with the contents of each of the corresponding columns, which we can see with this, call bracket I, bracket 1, bracket. However, if we look at what we do with this list of tuples immediately after, in this dictionary comprehension, we immediately destructure it, which begs the question, why are we bundling these together in a list of tuples? Why can't we just have 2 separate lists? Because it's a little bit awkward to have to index into our column to then append to sort of an empty list when we could just have a list of lists for the column data and a single list for the column titles. So that's exactly what we're going to do. So the first step is to basically get rid of the tuple in our list call and rename this to be titles. And then once we've done that, we've broken this code down here. So we need to add a second, what will be list of lists. And so we can construct this list, and we'll call it COLS for columns, initialize it to be the number of columns that we need. And now instead of having to do 2 indexings into this data structure, we can just do a single one. And the next change we can make is to sort of factor out this transformation that we're performing on the data that is t.text content. So we can factor this out into a lambda. And at this point, we can pretty clearly see that we can transform this nested for loop into a list comprehension, because we have the pattern once again. We're initializing our list outside here, and then inside that, we are calling append for every iteration of our nested for loops, which whenever you see this, you should think list comprehension. So the equivalent list comprehension is as follows. If you're not used to list comprehension syntax, this might be a little bit confusing, but once you get used to it, it's no more difficult to read than the nested for loops were originally. So we're basically constructing a list for each t in tr from the second element to the last element, and we are calling the format function on each of the t.text contents for the t's in the t.iterchildren. And note that we're also making a call, which is a bit tricky, to this function called zip, and then we're also using an asterisk at the beginning. This is the equivalent of a transpose in many other languages. So if we take a look at our Google Translate sort of function or algorithm comparison, you can see that in almost every single language and library, this is called transposed. Only in a couple do they call it something slightly different. So yes, unfortunate in Python that they don't have an explicitly named transpose function, but you can get the same behavior by just calling zip parentheses asterisk and then your two-dimensional collection and then end parentheses. So at this point, we're done. We've reduced our code from 60 plus lines down to, depending on how you look at it, roughly 10 lines, which is great. The question is, are we done? Can we do better? And some of you might have noticed that I have made a really, really big mistake. And that mistake is that I didn't pay close enough attention when I was Googling. Some of you might have been thinking even, I didn't do any of my HTML scraping with pandas. I didn't use pandas until I was constructing the data frame from the dictionary comprehension at the very end. And if I had been paying more close attention, I would have seen that right below this result, there was a pandas.readHTML method. And if we make use of this method, it turns these roughly 10 lines of code into 5 or 3 lines of code, depending on how you look at it. So this is extremely important. If you've seen any of my other talks about algorithms, I echo the point that has been made by several other individuals in other programming communities that you should know your algorithms. But not only should you know your algorithms, you should know your collections and you should know your libraries too. I think all of the work that I did refactoring the code that I worked on, it was useful. It was a useful learning exercise, and it's hopefully going to be useful, some of the things that I mentioned in this talk. But I could have avoided all of that if I had just known the Pandas API better. And I was just starting out with it, so I didn't know. So, it's okay that we make these mistakes, but over time, we should try to use our libraries and our collections and our algorithms as much as possible to avoid writing all this unnecessary code, whether it be 10 lines of code or 60 lines of code. Ideally, if there's a library with a single method that does exactly what you want, that's what you should be using. So if you want to go check out all of the step-by-step changes, there were 9 of them that I explicitly mentioned and then 2 of them at the end that I implicitly mentioned. You can check out the link at the end of this talk on my GitHub page. I have a file that has a Git commit history with all of the explicit changes if you want to see them sort of in the GitHub file diff mode. So we've finished step 1. On to step 2. This one's a lot shorter than the first step. As I said, this is only going to be about 10% of the talk. And so first we need to look at what does the HTML table that I've been referring to this whole time look like. So on the Codeforces website, for each contest, you can go to the status of each of the submissions, and it will show you all of the languages, whether they passed or failed, and for which problem in the contest they were submitted for. And so primarily we're interested in the column titled lang, short for language. But one thing you'll notice is that they don't just have a single submission option. If you are submitting in C++, you can choose several different compilers, C++ 11, 17, 14. For Python, they have the option to submit Python 3 or Python 2. There are various different sort of mappings from input or submission method compared to language. So the first thing we need to do is create a dictionary that maps all of the different submission options to the language that is being submitted in. Once we do that, we have a very short piece of code, 4 lines. We're importing pandas. We're initializing and declaring our dictionary mapping. once we've executed the code that we created in step 1 and stored it to a CSV, we can just load this as such. I was doing this for Codeforce's Educational Contest 74. And then once we have our data frame, we can access a single column in that data frame by going .lang. And then we can call the algorithm or method replace, which is basically going to do that transformation of mapping each of the submission methods to the corresponding language. And then we make a final call to value counts. So if you're familiar with the collection counter in Python, value counts is very similar. It basically is going to give you a frequency count of the unique elements that exists in a series or a list. So in Pandas and the Rapids Python API, this is called value counts. In the two Lisp dialects, Clojure and Racket, this is called frequency. And as mentioned before, in Python, it's not an algorithm, but it's a collection, but it has a very similar behavior. This is called counter. And so once we do this, we get the following output. So you can see there are 41,000 submissions in C++, 2,500 in Python, just under 2,000 in Java. And if we visualize this, it looks as follows. So overwhelmingly, the language of choice, at least for this contest, but it's typically the case for most contests, was C++ with 89% of the submissions. If we get rid of C++, we can see that the next top 3 are Python with 6%, Java with 4%, and C with 1%. And for what I will call the fringe languages, any language that had less than 1% of the submissions, the rankings are as follows: C#, Pascal, Kotlin, JavaScript, Rust, Go, Perl, D, Haskell, PHP, and Ruby. And second to last thing I want to mention is that if you are looking to accelerate your data science work that you are working on, and you have a bottleneck when it comes to performance, a lot of the times when you're using pandas, you can simply drop in replace QDF, which is the library that the NVIDIA's Rapid team works on, and your code will work. So this code works exactly the same as it did in pandas. It works in QDF, and it's just going to be a lot more performant if you're working with a lot of data and you have the GPUs to run this on. So if you're sort of wondering, well, pandas works for me, that's great. Keep using pandas. But if you do have a performance bottleneck, QDF can be a great alternative. And coincidentally, while I was on my run today, I typically like to listen to podcasts. These are the 5 that I was listening to. And one of them that I listened to just happened to be an interview with an individual by the name of Kyle Nicholson, who works at Capital One. And apparently they're using Rapids. And he mentioned in the podcast that for the sort of code that they were working with, the code base or the training model that they were working with, they had a roughly 30x reduction in cost and a roughly 100x speed up in the time to train their model. So it's extremely impressive the things that you can do with this Rapids QDF library if performance is a bottleneck for you. And if you're interested, check this out at rapids.ai. And the last thing that I want to mention randomly is a blog that was mentioned on a podcast called Python Bytes. This blog was entitled 8 Coolest Python Programming Language Features. The reason I'm mentioning it is that 5 of the 8 features, either directly or indirectly, were referenced in this talk, which I thought was kind of coincidental. So the first one was list comprehensions, which we used multiple times to refactor for loops. Generator expressions weren't directly mentioned, but they go hand in hand with list comprehensions. Slice assignment we didn't use, but we did use slicing to remove that one assignment to T and the call to the range function. Iterable unpacking, this is what I refer to as destructuring, where you are taking a tuple or a list and destructuring it into its individual components. And then dictionary comprehensions was being used at the end to construct our dictionary that we were passing to create a data frame. So a great article. I definitely recommend you checking it out. And yeah, hopefully you found this useful. Thanks for watching. I know it's a bit odd without having an audience and me just recording this by myself. And unfortunately, there isn't an opportunity to ask live questions, which is why there is an asterisk next to this. But if you do have questions, leave them in the comment section down below, or if you want, you can tweet them at me at code_report. I will do my best to monitor the YouTube comment section and to reply to any questions you have. And last but not least, all of the slides and the code that I've shown in this talk are posted on my GitHub page. So if you're interested, check them out there.